Okay, good morning, everyone. Hope you're well where you are. Welcome to the seventh of our series of lectures. For today, we're going to approach a pretty tricky subject, which is interferometry. But it's a very interesting topic, and I think it's going to be a lot of fun. So at the end of today's lecture, the idea is that you should have some concept of what complex visibilities are and how they relate to the interferometer baselines. You should understand how these visibilities are used to sample the UV plane and how an image of the sky can be recovered from this. And you should have a feel for what aperture synthesis means and how it's used in radio interferometry. So before we start, let me just I think interferometry for me still is a very conceptually difficult topic. And I'm not an expert by any means. The idea of this lecture is that by the end you should have some kind of intuition for what all of this means. So you should have some feeling for when I have visibilities in my dot, I have a set of visibilities. What do these visibilities actually mean, and how do they relate to the image that is the ultimate goal that I want to get out of my observation? So with interferometry, it has as much depth as you would want to delve into, and you can spend your whole career researching and understanding this stuff. So we're just going to have a very surface level description of this, but the main thing is that you have some overall intuition and feeling for how these things work. So before, let's do a quick recap of the most important concepts from the last lecture, which is these concepts of an aperture and the corresponding beam pattern. So an aperture has a technical definition, a complicated definition, but for our purposes, when you have a dish telescope that focuses light towards a receiver, we can define the aperture as basically the hole through which the radio signals are collected. And then the beam pattern is the diffraction pattern that the signals produce when they go through that hole. And this beam pattern is a Fourier transform of the aperture. So if you look at the picture on the left, if you have a circular aperture, then you get a diffraction pattern in this Bessel function. And basically this beam pattern tells us how sensitive the antenna is in different directions. So if we look at the beam pattern on the right, we see that we have major lobes where this telescope is very sensitive, and then some minor lobes off to the side where it's less sensitive. So it's a map of the sensitivity of the antenna. Right. Now, radio interferometry is based off an idea called aperture synthesis, and we'll get into some of the maths of how that works in a bit. But first, I want you to have some idea of what this means. So as we saw in the previous lecture, an aperture can be any possible shape. It doesn't have to be a hole, it can be any shape. The diffraction pattern will just be different. And it also doesn't even have to be a solid shape. So if you think about, for instance, a double slit diffraction experiment, you have two separate slits, but they produce, when light goes through it, it produces a single diffraction pattern. So we can have an aperture of any shape, and it doesn't have to be a solid shape. So if we extend this concept to its logical endpoint, we can think we can build, what if we build many telescopes kilometers apart, and light is incident on all of them at the same time, then they will still act as a single aperture with a particular diffraction pattern. So the idea of aperture synthesis is it's possible to put together the signals from many far apart telescopes in order to synthesize, which means to make up or to simulate a single aperture. So we have a large array of telescopes over many kilometers, but we regard them mathematically as a single aperture with a single beam pattern. So let's approach the simplest setup of this, which is a two-element interferometer. So let's say we have two dishes separated by a distance b. That distance is called the baseline. And say they're both pointing towards the direction S in the sky. Because they are offset by some distance, when a signal from the sky comes towards them, it will reach one dish slightly before the other because of the geometry. And so the time difference between those signals, the offset, we call that tau g for geometry. Now we're making some assumptions here. Let's say that this is a static system. So we're only interested in a single instant in time. This is not a dynamic thing. Let's also assume that the wave that's coming in is a monochromatic wave. So it only has a single frequency. And let's ignore any polarization in that wave. Let's ignore any distortions from the atmosphere, which could often be very significant. And let's assume that the antennas are perfectly identical. That's called a homogeneous array, and that they have exactly perfect electronics. We're ignoring any receiver noise or anything like that. Now, the electromagnetic wave that falls onto these two antennas has an oscillating electric field given by this equation. It's E, the amplitude, times a cosine, omega t, omega is the angular frequency, times time, plus a phase. And each dish measures a voltage, as we saw in, I think, the fourth lecture in the series. Each dish turns this wave into a voltage. And if we ignore the phase for now, the voltages that we measure are V1 is E cosine omega t, and then the second one is E cosine omega t plus tau. So now there's one of the voltages that has this delay caused by the geometry. And now we can define a quantity called the response of the interferometer. And you'll get to understand what this means exactly in a little bit. But first, let's define this quantity response as the average. That's what these square brackets mean, is the average of the voltage 1 multiplied by voltage 2. Easy. So if we substitute those equations, the cosines into this equation, we get this function. And these derivations are all in the textbook that I sent out, but I'm not going to spend time on the derivation. But if you multiply these together, this is the result that you get. You get an E squared times a cosine omega tau plus a cosine 2 omega t minus omega tau. So you see that there are two terms in this equation. The one on the left, the omega, is the angular frequency that's constant, times the geometric delay, which is also a constant. So this term is a constant, plus the second term is a cosine depending on the time. So this is a rapidly varying cosine function, which means that if we take the average of this equation, the second term is going to average out to 0. So we're left with the first term. So when we average over time, the second term averages to 0, and now the E squared, the amplitude, is equal to the power in the signal. Remember, the signal that we measure is the average of the square voltage of the signal. So we're left with this equation. The response is P cosine omega tau. Now omega, that's the angular frequency, and that's 2 pi times the frequency of the electromagnetic wave, which can also be written as 2 pi c over lambda, lambda the wavelength. And then the geometric delay is given by the baseline projected onto the source direction, b dot s over the speed of light. So if we substitute those in, we get this equation for the response, p cosine 2 pi b dot s over lambda. So this means that the response for a two-element interferometer is a cosine that depends on the power in the incoming signal that gives it the amplitude and the projection of the baseline with respect to the source. So the projection of the baseline means this B dot S. And when we talk about the projection of the baseline with respect to the source, essentially that means what does the baseline look like from the point of view of the source. If you imagine you have a source directly overhead your baseline, it sees the baseline in one way, but then if it moves off towards the horizon, that baseline gets foreshortened by the projection. So the important quantity is not the physical length of the baseline, it's what does the baseline look like to the source. So this is an example where you have a baseline of 10 times the wavelength. Then you get a cosine like this. If you have a baseline where the baseline is 24 times the wavelength, then you get a cosine that's much squished up. So the fineness of this response of the interferometer depends on how long your baselines are. For long baselines, you get a finer response, and the spacing between these response peaks, which we call the fringes, that defines the resolution of the interferometer, the resolution of the image that you're going to get out. It's kind of like if you think about the pixel in a television screen, the resolution, the detail that you can see in the picture on the screen depends on how small those individual pixels are. And the same with this. If you have the small fringes, the small response peaks, then you get a highly detailed image. So that's what this looks like in one dimension. You get this cosine. If you do this in two dimensions, you get a function like on the left, which is this kind of fan function, which spreads out from the center of the baseline. And if you do this in 3D, you actually see that it's more like a series of concentric cones. So this is what the response for the two-element interferometer looks like. But we should remember that the aperture, as we saw in the last lecture, modulates that response. So the aperture has its own beam pattern. And the beam pattern that we observe with the interferometer is actually this interferometer response, this fan function, multiplied by the aperture response. And if we have a circular aperture, then the response of the aperture looks like this, where you have a main peak, which is called the main lobe, and you have smaller side lobes off to the side. So if you combine those two responses, you get the ultimate beam pattern for this two-element interferometer, which looks something like this. It's a directional beam, but it has these fringes on top of it. Right. So now let's imagine that we are looking at some source using this beam pattern. So we are looking at a source that covers a solid angle omega on the sky. Now, the response of the interferometer is no longer just the product of the voltages. We have to integrate those voltages over the solid angle before we can do the averaging. And we use a double integral because it's integrated over two dimensions, right? Now, if you do the maths on this, and again, I'm not going to go through this, it's all in the textbook if you're interested, but it can be shown that the answer that you get from this is the double integral of I, which is the intensity of the sky in direction S, times this cosine 2 pi b dot s over lambda integrated over the solid angle. So now we have the result that the response of the telescope is related to the intensity of a source in the sky. So we have a link between intensity of a source or intensity of the sky and this response. This means that we can make a picture of the sky by measuring the response and then working backwards to get this intensity distribution. So that's the basic idea of radio interferometry. So now let's look at some examples from these are real VLA data, very large array in New Mexico in the US. If you haven't seen a picture of the VLA, it's shown at the top there. It's this array of dishes that are arranged into 3 legs, basically, of an interferometer. And if you use a baseline that's 1 kilometer long, so 2 dishes 1 kilometer apart, if they are arranged east to west, then you get these vertical fringes. If they are arranged north to south, you get these horizontal fringes. But if they're rotated, you get rotated fringes. So the orientation of these fringes is related to the orientation of the baseline. Makes sense. The length of the baseline, how far apart the telescopes are, determines how fine those fringes are. So if we use a baseline of 250 meters, we get very thick fringes of 120 arc seconds each. If we use a kilometer baseline, we get 30 arc seconds. If we use a 5 kilometer baseline, we get 6 arc second fringes. And this spacing with this, the width of these fringes determines the resolution of the image that we get out. So with Meerkat, we have a maximum baseline of 8 kilometers, which gives you about fringes of about 3 or 4 arc seconds wide. So the maximum resolution that we can get in a Meerkat image is about 3 arc seconds. So let's see what this looks like if we apply it to a real source. This is an example, Cygnus A. On the left, we have an actual picture of Cygnus A, and a real image using a full array. If we use only one baseline that's aligned east to west, and it's a 5 kilometer baseline, we get out an image like this. If we use a north-south baseline, we get out an image like this, where you only see these horizontal kind of cuts of the real image. So using a single baseline, you only see a small part of the actual source. And the idea with radio interferometry is you combine these baselines with different lengths and different orientations, that altogether each one is giving you a small part of the information in the full image. But when you put them all together, you get a full, complete picture of the sky. Right. So let's take a step back and think, what does all this mean? So a single baseline, which means 2 antennas, casts a cosinusoidal pattern on the sky that depends on its length and its orientation. What we observe with the telescope is the integral over space of the product of this pattern and the actual brightness of a source. We want to reverse this process. We want to take the measured voltages, which is the fringes that we can measure, the response that we can measure, and get back to the real brightness distribution of the sky, meaning to make an image of the sky. So before we can do that, I have to make a quick digression to talk about some mathematics that probably you've encountered in undergraduate and so on, but have forgotten. I know I've forgotten all about this, which is about odd and even functions. So in mathematics, there are odd functions and even functions. Even functions are symmetrical about the y-axis. Odd functions are anti-symmetric, so they symmetric but flipped upside down either side of the y-axis. And there's a theorem in mathematics that states that any real function, f of x, can be decomposed into an even function and an odd function. So if you have a function f(x) of y, f of x and y, then you can write it as a sum of an even function and an odd function, which are given by these equations. Also important to know is if you take an even function multiplied by an even function, you get back an even function. Odd times odd is also even times odd is odd, or odd times even is also odd. So why is this important? If we look back at this equation for the response that we got before, the intensity I is a real function that can have odd and even components. So we can decompose this intensity into an even function plus an odd function. And the cosine in this integral is an even function, right? A cosine is even. So if we take the odd part of the intensity and multiply it by the even cosine, we get odd. Which means that if we integrate the odd intensity multiplied by the cosine, we get 0. Because if you integrate over all space any odd function, the parts on the left of the y-axis and on the right of the y-axis are mirrored, but they're negative. So they cancel out when you put them together. So the integral of any odd function over all space is going to be 0. So this integral of the odd intensity is just going to give us 0, which means that this response RC cannot be the complete picture of the sky because it only contains the even part of the sky brightness. So if we want to get the full sky brightness, we need to use this cosine function, what we call the cosine response, RC, and we have to use the same function but with a sine instead, which we call the sine response, RS. So we have to use both of those. So RC samples the even part of the sky, RS samples the odd part, and we have to use them together to get the full picture. Now to get the RC, sorry, there should be the RS, the sine response, we take the cosine response and we add a 90-degree phase shift to one of the voltages before we multiply them together. So we can use the same voltages to get both the RC and the RS. And a complex interferometer, which is like Meerkat, is a complex interferometer, is one that uses both RC and RS to get the full picture of the sky. So let's now move on to a very important concept, which is the visibilities. So we can define a quantity called the complex visibility V, which is RC, the cosine response, minus I times the sine response. So now we have a complex number with the real part being the cosine response and the imaginary part being the sine response. And if we substitute the equations for the response into this, we get this equation. We get an integral over solid angle of an intensity I times this cosine minus I sine. And if we remember Euler's formula, if we see a cosine minus I sine, we can rewrite that into the exponential form, e to the power minus ix, which makes the maths more easy to understand. So if we write this equation in that format, we get a double integral over the intensity times e to the power minus I2 pi projected baseline divided by wavelength. And the cool thing about this is this starts to look very much like a two-dimensional Fourier transform. So I'm sure you've done Fourier transforms somewhere in your studies. If you haven't, or if you've forgotten, I very much recommend going back through your notes, trying to brush up on this stuff again. Fourier transforms are very important in radio astronomy in general, but in interferometry, they're absolutely crucial to understand. But the basic idea is this. So we have two functions, capital F and lowercase f, and these are a Fourier pair. They are related such that if you take the double integral of the lowercase f times this e to the minus I2 pi times ux plus vy, then you get back to the capital F. And if you do the set, substitute the capital F, you get back to the lowercase f. So you can convert between these two functions easily by applying this integral, and that's called a Fourier transform. Now, if we look at our equation for the visibility, it looks very much like a Fourier transform, where the visibility would be the capital F and the intensity would be the lowercase f. But it's not exactly the same, the right format, because we have this b dot s over lambda instead of a ux plus vy. So we have to rewrite this equation using a particular coordinate system to get it in the right format. So to get it in the Fourier format, we have to define the UV coordinate system. And that means we take from the telescope position, we define U as pointing east, and V is pointing towards the celestial north. Celestial north is towards the northern pole of the Earth's spin axis. So we define U and V, and then the direction vector S, which is where the telescope is pointing, is defined by its projections L and M onto the UV plane. And these are called the direction cosines. So if we have an angle alpha of the direction vector S with respect to the U axis, then L is given by cosine alpha. If we have an angle beta of the S with respect to the V axis, then M is the cosine of beta. And this means that we can rewrite this B dot S over lambda in the form UL plus VM. And if we substitute that back into the visibility equation, we can write it like this, which is the exact form of a Fourier transform. So this shows us that the visibility in UV space is a Fourier pair with the intensity in LM space. And this is called the central theorem of radio astronomy is called of radio interferometry is called the van Sittert-Zernike theorem, and it states that under certain conditions, the Fourier transform of the intensity distribution I of a distant incoherent source is equal to its complex visibility. Now, so this means that we can measure the visibilities with our telescope and then use a Fourier transform to get back to the intensity distribution, which is an image of the sky. Now you will note that there's a big caveat there, which is under certain conditions. And that's all of those assumptions that we made previously fall under those certain conditions. So the people who are real experts on interferometry will tell you that in reality, the relationship between visibilities and the image is much more complex than this. It's not really a Fourier transform, but for our purposes, for understanding what's going on here, it's useful to conceptualize it this way. To understand the relationship of how these visibilities relate to the image. So here are some examples in 2 dimensions. Say you have a brightness distribution on the sky that is 2 vertical lines, or 2, it's like a double slit. Then and the different colors show the two slits further apart. Then the visibility function is these cosines. That's the Fourier transform of those vertical slits. On the other hand, if you have a resolved uniform distribution of brightness, so it's just a flat brightness, then the visibility depends on the width of that uniform distribution. If you have a narrow brightness on the sky, then the Fourier transform is wide. If you have a wide brightness on the sky, then the Fourier transform is narrow. And the function of the visibility is the sinc function. It's called the sinc function. If you have a centrally peaked brightness distribution, so you have a high brightness in the middle, and then it falls off towards the side, then again the width in the visibility space is inverse to that of in the brightness space. So a narrow brightness gives you wide visibilities and vice versa. You can do this in 2 dimensions as well. So on the left is the brightness distribution, and on the right is the visibilities that correspond to that. So if you take the Fourier transform and its inverse, you can directly convert between these 2 images. If you have an elliptical Gaussian in the brightness, it gives you an elliptical Gaussian in the visibilities. If you have a flat disk in the brightness, then the visibilities will look like this Bessel function, where you have a bright central peak and then maxima and minima going out. Right. So next we move on to the concept of aperture synthesis, which I've already kind of explained what that means. But the notion is that a single baseline measures one single visibility value at a time, which translates to one intensity measure at a single point in space. So if you have a single baseline, you can only measure the intensity at one point in space. If you want to measure the intensity across a wide area, which is to make up an image, we need to first collect many visibility measurements on the UV plane before doing the Fourier transform. And we can increase the number of visibilities by adding more and more antennas to the array. So if we have n antennas in an array, the number of baselines is equal to half of n times n minus 1. And that corresponds to the number of points that we sample on the UV plane. And the more antennas that we add, the more of the UV plane is going to be sampled. And the more completely that the UV plane is sampled, the more closely the image that we get out will match the real thing. So the more antennas, the better quality the image, basically. An aperture synthesis involves using visibilities from many baselines with different orientations and lengths to form a single picture of the sky. So to understand this, let's go back to Fourier components a little bit. So on the bottom is an animation which illustrates the point that any shape can be reproduced by adding together sine waves of different frequency, amplitude, and phase. So if you look at this animation, it's taking a series of sine waves with different features and adding them together iteratively until eventually you get the Batman symbol out of it. And in order to make a good reproduction of the Batman symbol, you need lower frequency sine waves, big waves, to give you the overall shape the Batman symbol, you see it started over now. So you need the long wavelengths to give you the overall shape of the Batman symbol, and the high frequencies that you add give you finer and finer details to the ultimate shape. And the more signs that you add with a variety of wavelengths, the more exact the reproduction that you get out in the end. And if you the Fourier transform of the shape tells us exactly which signs we need to add together to get the shape. So that's how the Fourier transform relates to spatial information. Now, the same principle applies when we make an interferometric image of the sky. We need low frequencies, long wavelengths, which correspond to the short projected baselines that contain information about the large-scale structure of the sky. And we need high frequencies, which correspond to long projected baselines, which contain the information about the fine detail contained in a picture of the sky. And ideally, we want visibility spread out evenly across the UV plane to capture the spatial information on all scales, which means building a variety of baselines at different orientations and lengths. This is another illustration of this principle. So let's say, so on the left is the visibilities, amplitude on the left and phase on the right. And on the right is the image that you get out if you do the Fourier transform. So on the left, on the top, we are assuming we're only using the short baselines. And that means that the UV points that you sample are all close to the center of the UV plane. So close to the center of the UV plane corresponds to short baselines. And if you do the Fourier transform, you get a picture that's like very blurry. You can make out the overall image. You can see that this is a picture of a person wearing a hat, but you can't make out any of the detail. On the other hand, if you use only the long baselines, so you use only the visibilities far away from the center of the UV plane, and then do the Fourier transform, then you get back this image, which has all of the fine details. Suddenly you can see, oh, this person is wearing glasses. You can see his beard. You can even read the text on his shirt. But you can't make out really where anything begins and the next thing starts. So in order to get a full picture of this person, you need to combine the detail from the short baselines and the long baselines. You need the overall shape and you need the detail. So this is all to illustrate to you that the different points in the UV plane correspond to different scales of detail, different kinds of information that are embedded in the image. I hope that makes some sense. Here's an example, again using the very large array, which I showed earlier. So it's this array of telescopes arranged in these three legs. And on the right is the UV distribution of this array. So you can see the symmetry of this array, the actual symmetry of the dishes represents a measurement of the visibility as a function of U and V. V on the y-axis, U on the x-axis. And the more covered in dots that this space is, the more of the spatial information that we have recovered of the image of the sky, the more detail we are able to produce. So this is an example. If you use this UV coverage on the left, and you do a Fourier transform, you get this image on the right. And this is called the point spread function, or the dirty beam of the image. And you can think of that, this is the image that you would get if you were looking at a blank piece of sky with only a central point of brightness in the center, a single point source in the center. So you can see the point source in the center, but there's all sorts of weird patterns around here. And those correspond to places in the UV coverage which are missing samples. So because because so much of the UV space is empty, we don't have any information about the visibilities in these UV on this UV plane. There's a lot of information that's missing in this picture of the point spread function. Now let's look what happens if you allow this observation to integrate over an hour long. So you look at this point in the sky for an hour. And what you can see is that suddenly you don't have single points on the UV plane. They're starting to make these tracks in the UV plane. And that's caused by the rotation of the Earth. So as the Earth rotates around its axis, the source sees a different baseline. The orientation and length of the baseline changes, right? Depending on where the source is in the sky. And that causes the point in the UV plane that you sampled, the visibility, to move around. And so you get these tracks in the UV plane, meaning that the UV plane is more covered than it was using an instantaneous image. If we look at the instantaneous or snapshot coverage, there's less coverage of the space than there is after 1 hour. And now because we've covered more of the space, there's less of those artifacts present in the point spread function. So we get a better picture of this point source in the middle. You can actually start to make out that it's supposed to be a point source. Now, if we do this for 3 hours, we get even longer tracks and more of the UV space is filled out. And if we do the Fourier transform, you get an even better point spread function, where it's really starting to look like a point source now. If you do this in observation over a full 12 hours, now those tracks are starting to cover almost the whole of the UV space. And when you do the Fourier transform, you get a very nice round dot, which means that the point source is well resolved. But you can still see that there are these artifacts in the image, and basically you have to get rid of those using software techniques. So let's look at Meerkat, for example. This is how the antennas of Meerkat are distributed in space. So X and Y axes, and each dot represents one of the antennas of Meerkat. So you have a lot of antennas in the center, in the Meerkat core. I think it's 40 antennas in the core, and then more of them spread out. The maximum baseline is about 8 kilometers. Now, if we do the UV coverage of Meerkat, this is on the top left is the coverage over 15 minutes, over 2 hours, over 4 hours, and over 8 hours. So you can see one of the reasons why Meerkat is such a sensitive telescope is that it's able to cover a large part of the UV space in a short amount of time, even compared to the VLA. But you can also see in this UV coverage that there's better coverage close to the center of the UV plane. So it's darker towards the center here because there's more short baselines. There's more antennas in the core of the array. And then the further out you go, there are fewer and fewer antennas with long baselines. So you get sparser coverage in these far out regions of the UV space. And that means when you make an image, Meerkat is going to be very good at resolving the large scale structure of that image because the UV plane is very well covered close to the center, but it's going to be less good at resolving the very fine details. To resolve very fine details, you can use something like very long baseline interferometry, where you have antennas spread out over thousands of kilometers, and they sample the part of the UV plane that are very, very far away from the center and give you some very, very precise detail. Right. So let's get to some principles of how this actually works with imaging. So what I just showed you, the UV coverage and the Fourier transform of that UV coverage, that's called the dirty beam, also called the point spread function. So on the left here for Meerkat is some UV coverage, and on the right is the dirty beam for an 8-hour Meerkat observation. And you can see that it's a very nice resolved point source, but there are all of these weird tracks around the edges. You can change the shape of this dirty beam by applying different weights to the baselines. So for example, if you use natural weighting or uniform weighting of the baselines, you make them count equally when you do the Fourier transform, then you get different kinds of of dirty beams. And those different kinds of dirty beam can have different applications if you want to accentuate one kind of detail in your image over another. Depends on your purpose with the image. So if you convolve this dirty beam with the sky brightness, this is an example of the dirty beam convolved with a galaxy cluster in the middle here. So on the left is the UV coverage. In the middle is the dirty beam convolved with an image of a galaxy cluster. And you can make out the galaxies in this galaxy cluster, but there are all sorts of weird artifacts around it. And a big part of image processing with interferometry is removing these artifacts that are a result of the dirty beam. And on the right is the same dirty beam convolved with an image of the Andromeda galaxy M31. And you can see the same patterns. So this is another illustration of that. I think this is with, I can't remember which telescope this is with, but on the top left, you have the dirty beam, which is the Fourier transform of the UV coverage. And if you convolve that with the true image of the source, what the image actually looks like, this is the dirty image that you get back. So in a symmetric array, the dirty beam induces distinct artifact patterns that must be corrected for in the final image. So in the next lecture, is going to be a lot about how you go from the image, which is the illusion of the dirty beam with the true image, to remove those artifacts to get back to a clearer picture of what the actual object looks like. So all of this so far has been a pretty idealized case of an interferometer. In reality, things are, of course, much more complicated. If you think about it this way, a short baseline can be a few meters away from one another, and the delay that we're talking about from one antenna to the next is the time it takes for light to travel between those two antennas. And light travels at 300,000 is it kilometers per second, or yeah. So the amount of time that it takes to traverse between those two antennas is going to be minuscule. It's going to be microseconds or nanoseconds. So if you want to do interferometry precisely, you have to be making account for effects that are operating on millisecond, microsecond, nanosecond scales. So even a very small effect like the atmosphere inducing some aberration on the light is going to cause delays that are comparable with the delay from the geometry. And you have to account for each and every possible little delay that could exist in your system, all the way from the ionosphere to your electronics, which it's very difficult to time things exactly so that they work on nanosecond scales. So all of these things need accounting for. One of the big things that you have to take account for is something called delay tracking. So in our examples here, we've assumed a static case, right? But in reality, as you observe an object, the Earth rotates with you, causing your target to move across the sky. So in order to keep observing a source in the sky, you have to steer the fringe pattern accordingly so that it moves towards the target. And in order to do that, you have to add precise delays to the voltages, which is called delay tracking. So this illustration on the right shows on the top what you can do with delay tracking, where you change the orientation of the fringe pattern. On the left is what happens if you don't do delay tracking. If you don't add those delays, then you get much reduced sensitivity of the telescope as you go further from the zenith. But even if you do delay tracking, this delay tracking only actually works perfectly for sources at the phase center, at the center of this main lobe. For everything else that's further away from the phase center, everything is going to move slightly with respect to the fringes, causing a loss of sensitivity. So there's always going to be losses involved with interferometry. Another important factor is that we assume non-monochromatic waves. So we assumed a monochromatic wave with a single frequency, but radio waves actually don't consist of a single frequency, but are the superposition of a range of frequencies. Now, typically, before we analyze the signal, we apply what's called a bandpass filter, which removes any frequencies outside of a certain range, leaving only a finite bandwidth to consider. So, for example, if you've Meerkat as an L band, a UHF band, and an S band receiver, so the UHF band uses a bandpass filter that only allows frequencies from 544 megahertz to 1088 megahertz, if I'm remembering the numbers correctly, and everything outside of that it throws away. And the effect of considering a finite bandwidth, delta nu, is that the visibility function actually changes. So you get the visibility is now the intensity multiplied by the to the exponential here, but then you have an extra sinc factor. Sinc function is sine pi x over pi x, which is so you have a sinc function, which is a function of the delay times the bandwidth, delta nu. And so the effect that this has, if you look in the diagram on the bottom there, that's what a sinc function looks like. So if you add this factor to the visibility, the effect that it has is that it reduces the sensitivity of the telescope towards the edges of the field of view. So it reduces the field of view. So you're only actually able to see a smaller part of the sky at once as a result of having a finite bandwidth. Right. So that's it for today. The next lecture, we're going to get more into how these images are processed and different calibration methods that are needed to get exactly the image that you want out of it. So today was just a very simplified picture to give you some understanding of what these quantities mean and how they actually relate to one another. So to summarize, a single interferometer baseline casts a sinusoidal pattern on the sky, which is called its response, which depends on its length and its orientation. A complex interferometer measures a complex visibility, which has this cosinusoidal pattern as its real part, and the pattern offset by 90 degrees as its imaginary part. That's the sinusoidal response. So we measure a complex visibility, right? The brightness of a point in space and the measured complex visibility are a Fourier transform pair. We can convert between the two using a Fourier transform. And in order to map an extended portion of the sky, we need many visibilities, which corresponds to many different baselines, which we use collectively before we do the Fourier transform. And the more completely the UV plane is covered by visibility measurements, the closer the image will be to the real thing. Right, so let's move on to some questions. There are already some in the chat, which I'll address in the meantime. So Raul asks, why do we have the term plus tau g instead of minus tau g? Yeah, okay, so let's go back there. So this is when you do the response for a single baseline. One voltage is offset by a factor tau g. And here I'm using plus tau g, but it could be minus tau g. It's just a matter of convention. It's not going to change the maths at all whether you use a negative or a positive, because if you look at the equation below it, this cosine falls away anyway. So you're left with only this constant value, cosine omega tau. So it's not going to make a difference. But you could equally use a negative or a positive. What do the dimensions mean in resolution? In other words, 1 dimension, 2 dimension, 3 dimensions. So this is referring to this, I believe. So the response in one direction is a cosine, meaning if we look at the baseline from the side, from one dimensions, what is the response going to look like? Two dimensions means what is the response going to look like if we look from the top. So you can see both directions, x and y, or u and v in this case. And in three dimensions means if you were to look from outside, what would the response actually look like? So they just the three-dimensional one is the real response, and the two-dimensional and one-dimensional responses are just projections onto one or two dimensions. Does that answer your question, Raul?
Yes, sir.
Okay. And then what is the sky brightness distribution? Is it a specific intensity? The sky brightness distribution just means what is the brightness of the sky, or the flux density, if you want to put it that way, at a particular point in the sky. So if we make a map of the sky brightness, then that is the same as making an image of the sky. If you think about a digital picture, it's just an array of values with brightness and color corresponding to each pixel. And so this is the same thing. You just have the distribution of the brightness at any point in the sky. Does that make any sense, Raul?
Yes, sir.
Okay. And then why do we need a bandwidth filter? So yeah, so we have to remove frequencies above and below a certain value for some technical reason to do with how the antenna actually receives those signals, which I can't think of the top of my head, but it makes sense. You can't consider an infinite range of frequencies, right? Because we're working in a digitized environment where you can only sample a finite range of frequencies, and you have to decide which range exactly to work with. But that's a good question. I can't think of it off the top of my head. It must have something to do with the particulars of antenna theory. But I can look that up and maybe get back to you with a better answer. Okay. So Jufar asks, why is UV very important for the quality of images produced by radio interferometers? Okay. So the UV coverage tells us what scales of information in the image has been sampled, right? If we think about this Batman symbol animation, if we only use a small number of these frequencies, then the symbol doesn't resemble the Batman symbol very well, right? The more that we add together, the finer details you're able to reproduce in the reproduction of the Batman symbol. And the same applies with an image of the sky. You need to sample spatial frequencies at you need to sample a wide variety of spatial frequencies that each contain some information about the picture. It's the same principle as with this Fourier transform that I showed of the person with the hat. If you only use a part of the UV plane, if you only have some UV samples on a part of the plane, then there are some scales of information in the picture that you're missing out. So if you only use short baselines, you only cover a small part of the UV plane, then you're only going to have information about the large scale structure of the image. You're going to be able to resolve some big features of the galaxy that you're looking at, for example, but you're not going to be able to see any details within it to make out what is the structure of that radio galaxy. And on the other hand, if you use only UV samples far away from the center with long baselines, you can see some detail, but you're not going to be able to resolve the overall structure. You're going to be able to see some fine details of the galaxy, but you're not going to be able to see the full galaxy as a galaxy, if that makes sense. So, Jafar, does that answer your question? Why is UV coverage important in the quality of image?
Yes, thank you. Thank you.
Okay.
That's a good answer.
Cool. And then what is the definition of the point spread function? Is it a function of how each point in the image is spread in the sky, depending on the baseline distances or not? Yeah, so I think a function of how each point is in the image is spread in the sky is a good definition for it. The basic way that I think about this is, what would the image look like if I were observing a single point source in the sky? If we had a completely blank field except for a point source, then what we would get out of the image would be this point spread function. And conversely, if we are observing a complicated field with all sorts of stars and galaxies and so on, each point in that image is going to be convolved with this pattern. It's going to have this pattern superimposed onto it. So the image is the convolution of the point spread function and the real image of the of what the source actually looks like. Yeah, Kevin, you have your hand up.
Yeah. So is it fair to say then that if you're going to use imaging or take an image of something using interferometry, that firstly that it has to be pretty big by comparison? I mean, I missed the when you got the Fourier transform of the dirty beam, the scale of the UV plane, right? That's the baselines. I didn't see exactly what it Fourier transformed to, but that would be the field of view, right? Effectively. Does that make?
So you're talking about, say here, we have the Fourier transform of the visibility is convolved with some brightness distribution.
Yeah, and I think the next that one over there.
Yeah.
Actually, there was a different one which you had the scales of the UV plane on. But anyway, I mean,
yeah.
Is it necessarily the case that the object that you're looking at? Oh yeah, that one, I think.
Okay.
If you want to make an image, that it has to be fairly large for that UV coverage to take an image of it in the first place.
Well, no. Well, it depends on how wide the UV coverage is, but remember that the scale in the UV plane is inverse to scale on the image plane. So if we have a wide coverage in the UV far away from the center, that actually corresponds to a small part of the image. So if we have wide long baselines, we can actually resolve a small part of the image. And that's why the maximum baseline is what determines your resolution in the image. If you have long baselines, UV coverage far away from the center, you can resolve a small point.
So you could, in theory, then use imaging or interferometry to take images of what are essentially point sources.
Yeah, exactly.
Yeah, okay.
If for using BLBI, we have these antennas spread out thousands of kilometers apart. You can make out details in an image that corresponds to micro arc seconds. So in nature, there's no real point source, right? But you can make an image of a radio galaxy or something and focus in on an extremely, extremely fine detail of it. And that's one of the ideas with expanding radio interferometry in the future, could be to build antennas on the moon or in space, and then use those extremely long baselines to resolve unimaginably fine details.
But the second part is then it would have to be relatively static in time-wise, though, would it not? If you're going to spend 8 hours taking an image of it, are you assuming that the thing doesn't change very much over 8 hours?
Yeah. So for if you're taking an image over 8 hours, naturally you're averaging it out. So if there's any kind of change inherent to the object in 8 hours, you're not going to be able to see it.
Mm-hmm.
For the most part, that's a pretty acceptable kind of assumption to make. If you're looking at some galaxy somewhere, there's not much that's going to change in 8 hours. But if you're talking about transients, you can't take an 8-hour image of a transient because you're just going to smear it out entirely. But yeah, for the most part, that's a safe assumption to make.
Okay. Oh, thanks.
Cool. Okay. Any other questions about this stuff? It is to me, it still feels like black magic to a large degree. The idea that you can measure voltages and then turn that into a picture, I still kind of struggle to even conceptualize how that works. So I encourage you to just spend some time thinking about this. If you have a data set of your own, look at your UV coverage that you have, look at the dirty beam, try to understand physically what this stuff means. But the important thing, if you understand this concept of the UV space, if you understand what visibilities are, then it's going to make your life a whole lot easier. So just make sure that you kind of have those ideas firmly in your head, and then you can always kind of look up the details. Okay, so that's it for now. If there's nothing else, we'll talk again in 2 weeks' time. Okay. Okay. Thanks everyone, and cheers, and see you all again.
Cheers.
Bye.
Bye bye.